Let's talk a little bit about nuclear power. This is a diagram for I think this is a light water reactor or something like that. This is a Fukushima style reactor. This is what we had at 3 Mile Island. These are the reactors that we use here in America, right? And one by one, we've been shutting these things down. Interestingly enough, I think France generates something like 80% of their electricity using nuclear power. We generate a small proportion of our power with nuclear power. Let's just talk about how it works, and then we can talk about a little bit about the pros and cons of this, right? But this is the containment vessel right here. Okay, this is made of strong stuff. It's concrete. It's got like I think a stainless steel core or something like that, right? And this is the radioactive stuff. So this is fuel, and then there's also a moderator in there. Okay. And a moderator is something that slows neutrons down. If the neutrons are going super fast, they actually don't cause a fission reaction. They just go right through the nucleus without sticking to the nucleus. And you want them to stick to the nucleus to cause the reaction. Okay, these are control rods. So that's something like cadmium that just absorbs neutrons. You put them in, and the reaction shuts down. Now, of course, the problem with this is if the core melts, you can't get the control rods in, right? We've got a little problem there, right? And what we do is we've got water, and this is the water that you definitely don't want to drink this water. This water is kept under super high pressure, so therefore its temperature can be higher than the boiling point of water at 1 atmosphere. And this stuff could have little bits of uranium and plutonium and stuff in it, but we pump that in a specially shielded thing. We pump that around into a tank, and this water could be from the Willamette, okay? This, I wouldn't want to drink this water either, but, it's ostensibly safe as long as this doesn't leak. And this water is used to boil the secondary thing. So we have these two controlled loops here so that we don't let much radioactivity out into the atmosphere. And we boil this, and then this is just a standard steam turbine electric generator. The condenser is something that just cools it down. And this is where the Willamette is going to flow through here, right? This is, probably Bull Run water. This is Willamette water to cool down our condenser. Okay, this could also be a cooling tower. Like you've seen those big things that look like this by the nuclear power plants. Okay, this could be a cooling tower. This could just be a river. I think Trojan used just our nuclear power plant in the Northwest. Just used the Columbia, I think, to cool itself down. Okay, because an engine needs a hot side and a cold side, right? So this is the basic idea. And the problem with this is, of course, you've got to keep this core cooled. I think in Fukushima, this pump ran out of electricity, and then these containment vessels boiled and burst. That's not good. Okay, but this is the basic idea. These are fairly safe, and if they had the latest technology, if they had backup generators, et cetera, it wouldn't have been as disastrous. But they didn't. Okay, let's just take a look at this is sort of a typical problem. Okay, an 820 megawatt plant is 30% efficient. How much uranium will it use in a year? Well, let's figure out the total power output. Okay, so the power output is 820 times 10 to the 6th watts. That's joules per second, right? And then in a year, there's 365 times 24 times 3,600, right? 365 days, 24 hours, 3,600 seconds per hour. Right, so this will give us our total energy output. Oh, my batteries are low. Uh-oh. Got to clear that. Okay, so let's see. 820 e to the 6 times 365 times 24 times 3,600. I just took this off an IB test. Okay, so this is 2.85. Oops, I'm dyslexic here. 2.586 roughly times 10 to the 16th joules, right? That's our power output, right? So 0.3 is equal to output over input, right? So let's see. Is that right? Yeah, that's right. Okay, so 0.3 is equal to 2.586 times 10 to the 16th over the power input. And then how do we do that? I think we just divide this by this, right? So our power input is going to be this divided by that. Okay, so divided by 0.3. And so our power input, and this is what we have to figure out, we have to reconcile, is 8.6198 times 10 to the 16th joules, right? Okay. So that is our total power input, and every atom we're going to assume is 200 MeV, right? So Avogadro's number. Okay. So now we have to figure out how much energy that is, right? So let's figure this out. Let's figure out how many atoms that is, right? Okay. So 200 MeV. Whoops. 200 times 10 to the 6th times 1.602 to the minus 19th. Let's figure out how many atoms we have to use to get that much energy, right? Okay, so 200 E6 times 1.602 E minus 19 is still not very much energy. Every atom is 3.204 times 10 to the minus 11th joules, right? So let's figure out. It's going to be a tremendous number of atoms, but we can handle that, right? So number of atoms is this much energy divided by this much energy per atom, right? So it's going to be times 10 to the 16th divided by, let's figure this out. Okay, so that guy, this is going to be a tremendous number divided by, sorry, I said tremendous. It's going to be incredibly huge. All right, and so that number of atoms, it's going to be, the N is going to be 2.69 times 10 to the 27th atoms, right? Let's figure out how many moles. So let's divide that by Avogadro's number. How many moles is that? Okay, so divide that by 6.02 E23. There's lots of ways to do this. That's a lot of moles. That's 4,468.99 moles. All right. And then we have to multiply that by grams per mole, and this is roughly 235 grams. So I'll say 0.235 kilograms, right? I could be more precise. I could say 0.235043923, but I'm too lazy. Okay, so times 0.235, and I get that it's 1,050 kilograms. Let's just say that if it was burning coal, that it would burn more coal than that. Okay, there you go. How's that? All right.